As Gabriel said, I will be speaking to you about neural coding, and in particular about two complementary questions. Number one, if we know what a stimulus is, as presented to some nervous system, how well can we predict what the response of a neuron that's a member of that nervous system is going to be? And sort of the flip side of that question, if we know what a neuron or a population of neurons have done in response to a stimulus, how well can we infer what that stimulus was? In other words, can we decode the neural code? And a more overarching sort of meta question that I'd like you to keep in mind is, if we can do these two things, if we can answer these two questions, how well can we say that we understand neural function, that we understand what the brain is doing? So here's an overview of the subjects that I'll be covering. I'm not going to read through it, but it'll be coming back frequently. The first subject that I'm going to touch on is very basic, just techniques for characterizing neural responses. So a delta function is a function that is zero almost everywhere, except at zero. We can describe the spike train rho as a sum of these delta functions. So rho as a function of t is just the sum of delta functions shifted by t sub I for I spikes. And that might look something like this. The overall firing rate of a spike train rho is then simply the number of spikes fired divided by the time window under consideration. And generally in neuroscience experiments, we are presenting a stimulus multiple times because individual neurons are not deterministic, or at least not at the level that we can access. And so multiple repetitions are typically needed to properly understand how a neuron behaves. So we can average across multiple stimulus presentations. And throughout, these angled brackets denote the average or the expected value. So the mean firing rate in response to a stimulus is just the mean number of spikes fired divided by the length of the time window. Now, brains do interesting things, and the neurons that make them up do interesting things, such as varying their firing rates. So we will oftentimes be interested in firing rate as a function of time. One way of accessing that is to take a window, W, and slide that along, convolving the window with a spike train to give an approximation of the firing rate at a given time. At perhaps the most basic level, such a window function could be just a rectangle. If we're interested at the firing rate at time t, denoted by this dashed line, we count up all the spikes in this window, divide by the width of the window, and that's our estimate at time t. A slightly more sophisticated window might be a Gaussian curve, in which we weight action potentials closer to time t more heavily. Now, both of these techniques are what's called acausal, which means they incorporate spikes after the time question. So one thing that you can do is limit your consideration at time t to spikes that happened before time t. So one example is this rectified exponential. So here's an example of a sort of idealized spike train, as we discussed previously, sum of delta functions. And this is actually computed from a real spike train in an actual MT neuron while a monkey watched a video. So if we want to know what the firing rate profile of this neuron during the 3 seconds of this trial looked like, perhaps the most basic thing we can do is to bin the spike train. And that's what's done here. It's been divided up into 100 millisecond bins. And this first 100 millisecond bin, sorry, I had a little too much coffee today. This first 100 millisecond bin, there were 5 spikes. And so 5 spikes in 100 milliseconds implies a 50 hertz firing rate. The next 100 millisecond bin had 9 spikes, so we had a 90 hertz firing rate. And so on for all 30 bins. Now, if we actually, rather than just using a rectangular bin, use a sliding rectangular window, the profile looks considerably different. We start to see a lot more structure, and this estimate is more sensitive to rapid changes in firing rate. Here we see the results when we use a Gaussian window, as described on the previous slide. And here we see the results with a causal rectified exponential filter. These two, you may note, look quite similar, except the estimates here, the peaks and troughs and other features of this estimate, are all shifted in time slightly later than they are here. And again, that's because this estimate is only considering spikes that came before time t in the calculation of the firing rate at time t. So, those are sort of the basic ways that we can talk about what is a neuron doing, how often is it firing, what does a spike train look like. Typically, we're interested in what a neuron does in response to different stimuli. And the description of a firing rate as a function of stimulus is called a tuning curve. So one basic and classic example comes from monkey V1, primary visual cortex. So if you present an oriented bar moving with the direction to the receptive field of a cell in V1, you might not get any spikes. You might get a few spikes. You might get a lot of spikes, all depending on the orientation of the bar relative to that cell's preferred orientation. And it turns out, if you plot firing rate as a function of orientation, that's what's shown with these dark circles here, you get something that looks an awful lot like a Gaussian. And so one can fit a Gaussian to these points and thereby describe how this particular neuron responds as a function of the stimulus. So firing rate is a function of the stimulus. Yeah?
I have a quick question on the previous slide.
Mm-hmm.
This one. So what are the pros and cons, I guess, of using some of these? Because like a Gaussian seems kind of intuitive, but then like a rectifier shifts it in time, which may or may not like be how the brain does it. So like what?
Right. So a non-causal filter, in other words, one that incorporates future spikes in the estimate of the firing rate at a given time, is a little bit strange because the brain doesn't know what future spikes are going to be. So if you're trying to describe things as the brain sees them, you might want to use a causal filter, such as this bottom one. On the other hand, spike rates are typically autocorrelated, so the spike rate at a given moment is going to be quite similar to the spike rate at the next moment. And so you can actually typically learn useful information by incorporating a larger window around the time. So it largely depends on the application. And I mean, one thing that you can see here versus here, just so that this Gaussian had a standard deviation of 100 milliseconds, and this rectangular window had a width of 100 milliseconds. And of course, with a standard deviation of 100 milliseconds, the overall kernel is broader than that. And you can see that some of the details, like these two spikes here, elicit this distinct, whereas here it's just sort of very low plateau. So you do lose some temporal precision depending on the width of your Gaussian. So that parameter is another thing that's going to depend on what exactly you want to use your firing rate estimate for. So I'm not sure if that answered your question, but
yeah, it seems like there's a lot of choices.
There are a lot of choices, and it's often a question of trial and error, figuring out what works best for whatever you're trying to accomplish. And we'll get a little bit into what things one might try to accomplish with firing rate a little bit later. So another example of Gaussian tuning curves comes from a little higher up in the visual hierarchy. So this comes from an experiment by Poisson and Connor, recording cells in monkey V4. And they used a stimulus set that was parameterized along a few different dimensions. Two of them shown here are the orientation of these little arc shapes within the receptive field and the curvature of the ends of the arc. So here the curvature is very high, and as you get down here, the curvature is very low. And here they've plotted curvature, they've plotted firing rate, or normalized firing rate, as a function both of curvature and angular position. So this is actually a two-dimensional Gaussian. Then you can throw in more dimensions if your stimuli have more dimensions. So the limit is basically your ability to handle mathematics and the computational power that you have at hand, as well as the density with which you cover space. So one thing suggested by this angular position, and actually in fact suggested by this angle here, some stimulus dimensions are cyclic rather than linear. So in some cases, it may make more sense to fit a sinusoidal tuning curve rather than a Gaussian. So here's an example from monkey primary motor cortex, where the monkey was moving his arms in 8 different directions. And you can see that in some directions associated with that movement, there was a lot of firing, and in other directions, there was little firing or even suppression. And so the firing rate was plotted as a function of movement direction. And you can see 0 and 360 degrees are the same direction, and the sinusoid fits quite nicely. And here, this is modeled as just one cycle per cycle of the stimulus, but that need not always be the case. So this comes from experiment in which recordings were made in monkey IT in response to these sort of abstract paperclip symbols. And this particular cell responded with a peak at negative 120 degrees rotation, and then also another peak at 60 degrees rotation, sort of the quasi-mirror image, which is something that you see pretty often. And the curve shown fitting here is not exactly a sinusoid, but you can see how a sinusoid might do a reasonable job. Yeah?
With these kinds of experiments, like how fixed is the spike rate for a given stimulus instance? Like why is it actually like at 64 hertz? Like if you put a speaker on it, you would hear like a buzz 64 hertz?
It would sound more like, but yeah, I mean, it's neurons in monkey IT can fire up to a couple hundred hertz.
I guess is there any frequency variation? Like if you were to plot the spike rate over time, it would be like a flat line.
So again, there's tremendous variability in the firing rate profile. The eraser doesn't work so well. So one very common thing that you see is an initial transient followed by some other stuff happening, and that other stuff may be a sustained period elevated beyond baseline, maybe a dip in firing rate. Other times, there's more of a ramping up in response that is more sustained. Sometimes there's just a burst of firing, nothing. There's tremendous.
After some, the conditions are, you measure the spike rate after some time after presenting the stimulus, maybe, like for this plot, for example.
Sorry, I missed the first few words you said.
You measure this is the spike rate after some time.
Right, yeah. So all of these examples are looking at spike rate just as the count of spikes divided by window length for some window after stimulus onset. The particular window varies by experiment and by brain region. Later on, maybe in 45 minutes or so, we'll look into how to use individual spikes to better understand the characteristics of response. But much of the coding and decoding work that we're talking about today will involve just spike counts. Yeah?
So the neurons have like a base firing rate, so where would that be? So a negative, I mean, going below a certain level means something. It's not just when it spikes up, it's spiking.
Right, so many neurons have a baseline firing rate, and they can be inhibited, as you see in this example. So here things are clicking along at the baseline rate, and then an unpreferred stimulus comes on and actually suppresses firing rate. So yes, that can be important. There are also neurons whose baseline rate is, for all practical purposes, 0, and only respond presented with stimulus. And yeah, so depending on how you're characterizing the neural response, that may or may not be useful or obvious. But it's definitely something to be aware of. So this slide may look familiar. This is a nice study. This is just showing an example, but in the context of this lecture, this is just showing an example of another type of tuning curve. And as Gabriel mentioned, this is actually a behavioral tuning curve rather than a barometric tuning curve. But it's a sigmoidal tuning curve. And these are useful in cases where behavior or neural firing rate starts off at some baseline level and then increases through a dynamic period or dynamic range and then plateaus at some peak level. So I won't get into the experiment itself because you've already heard about it. But basically, the behavioral data are well fit by these sigmoid functions. So that was characterization of firing rates as scalars as a function of stimuli. So that leads to a question, well, what are good stimuli? How do we elicit high firing rates? Or actually, I guess I'm going to present it as two, but it's really one nice technique for figuring that out is using the spike-triggered average, which turns out to be essentially the same as reverse correlation. So the intuition for the spike-triggered average, denoted here as C, is the following. Say here's a spike train, a very simple spike train. There are 3 spikes shown. 1, 2, 3. And this is a stimulus. In particular, this is a one-dimensional stimulus. What it is isn't so important. It could be contrast, it could be velocity, it could be size, something that varies along one dimension. And at these 3 time points, this rapidly changing stimulus elicited 3 spikes. So what you do is you take some window and you look at the stimulus in that window leading up to each spike. And you simply take the average of all of those windows. So this window plus this window plus this window. And if you do that for these 3 spikes plus many other spikes that aren't shown, you might arrive at a spike-triggered average that looks something like this. And what this tells us is that as time preceding a spike gets closer and closer to that spike, immediately prior to a spike, there tends to be a strong dip in the stimulus. And presumably, that might have something to do with the elicitation of that spike. So this is just the formulation of what I described heuristically here. C here, again, is the spike-triggered average, and tau is the time before the spike.
How do you interpret the stimulus before a spike?
Say that again?
How do you interpret the stimulus before the spike?
So the interpretation here is, for the spike-triggered average, is that this is the kind of stimulus that best elicits a spike. Now, one caveat to that is you can only evaluate that for stimuli tested. So doing this properly involves covering the entire range of stimuli evenly and comprehensively. But if you've done that, then this average should approach, under a few assumptions such as linearity, should approach the optimum stimulus to elicit a spike. So another way of looking at the spike-triggered average ends up being called the reverse correlation. And so first of all, let's just define the correlation between stimulus and the response, also known as the rate-stimulus correlation. So this is just the correlation between the firing rate at time tau and the firing rate at time t and stimulus at time t shifted by some offset tau. And it turns out that the spike-triggered average is functionally equivalent to reverse correlation, so-called reverse correlation because of the negative sign here. So here's an example in which an electrical current was applied to a neuron whose responses are shown here in the lateral line system of the weakly electric fish, which picks up electrical fields. And you can see that there's some action potentials fired. And again, by calculating this reverse correlation, they were able to infer what the optimum stimulus was to elicit a spike from this cell. And you can see that there's some positive voltage followed immediately before a spike by a sharp negative voltage. And as I sort of alluded to a moment ago, reverse correlation, spike-triggered average, is most useful when your set of stimuli actually covers all possible stimuli. Yeah?
Do you have a sense of how gracefully this fails when, probably neurons are mostly nonlinear. That's not a super useful thing to do. So do you have a sense of how gracefully this fails when things are nonlinear? And can you get a sense of what kind of I don't know.
So this is much more sensitive to the parameters of your stimulus set than to the details of neural response. But it can be sensitive to that as well, and soon I'll show you at least one basic technique for overcoming that. Yeah?
So this seems to, you've shown examples of where this works on one-dimensional stimuli. Is there any way of generalizing this to dimensions?
And I'll get to that soon. And it's very straightforward. But another thing that's useful for reverse correlation is for the stimuli to be uncorrelated in time. So this stimulus, for example, is not uncorrelated in time. It's not a white noise stimulus. But if it is a white noise stimulus, then calculations get easier, and I'll come to what I mean by that later. So you can also use reverse correlation to probe temporal dependencies in spikes. So here's an example in which reverse correlation was used to find the mean stimulus leading up to one spike and the mean stimulus leading up to two spikes separated by approximately 10 milliseconds. And you can see that these average stimuli are quite similar. But if you instead look at the average stimulus leading up to pairs of spikes separated by approximately 5 milliseconds, then the average stimulus leading up to that looks rather different. And so this tells you that while seeing a couple of spikes separated by a fair amount of time may not mean much, if you see two spikes very close together, that's probably an indication that there was a much higher value stimulus. And you can get as fancy as you want with your triggers for reverse correlation. So yes, reverse correlation works beyond one-dimensional stimuli, and it also works beyond spikes. So this is an experiment in which the triggers for reverse correlation were not neural spikes, but were actual behavioral responses of people looking at these two-dimensional arrays of visual white noise. And subjects were asked to press a button when they saw an S in that white noise. And they did this many, many times. And here, this little subpanel A shows what's called the classification image, the average stimulus that elicited a report of an S. And you can maybe see very faintly an actual S here. And if you blur the stimulus and then threshold it, you can see maybe a little more clearly the outline of an S, and it matches rather well an actual S from a database of images of S's. So it's a very, very powerful and very widely applicable technique. Yeah?
So let's say you want to recover the preferred stimulus of a V1 neuron, right? Mm-hmm. And there's these simple neurons that, like Gabor profiles, that have specific phase relations. And then there's these complex neurons that like a certain orientation or frequency, but don't care about the specific phase, right? So with reverse correlation in, pixel space, would one be able to recover a Gaussian that can be either like positive here and negative here, or the other way around? And
so it depends on how you construct your set of test stimuli. So if you used two-dimensional spatial white noise such as this, then you should be able to recover a Gabor filter. It's not clear to me that you would be able to recover anything from a complex cell. However, if you instead used Gabor patches of varying orientations and frequencies and phases, then your complex cell, actually phases might confuse things, but if you used varying frequencies and orientations, then reverse correlation based on a complex cell's firing rate should give you that cell's preferred orientation and preferred spatial frequency.
So it depends a lot on how you parameterize the input space.
Absolutely. So, yeah, I mean, it's much more likely to work if you know something about the sort of stimuli that the cell might prefer, rather than just throwing everything at it, because everything is a very large space. Okay. So up until now, we've talked a little bit about how to describe what cells do and what they like. Now, in many cases, you may want to be able to generate your own spike trains, either for testing some software, for building a model, or for perhaps even running some theoretical analyses on what networks of neurons may do. So a little bit of background first. A point process is a stochastic process that generates a sequence of events. And by a stochastic process, I mean a set of random variables indexed by time. A renewal process is a particular kind of point process called a renewal process because the probability of an event is uninfluenced by anything that happened prior to a previous event. So if you're trying to figure out whether to have an event, you look only at the most recent event, and that guides you. And a Poisson process is a point process, which is a renewal process, but in fact has no dependence on any previous events. So in the context of this course, these point processes are going to be spike trains, and whether or not you fire an action potential is potentially, in the case of a Poisson process, going to have no dependence on what happened previously, or in the case of a renewal process, may depend on the time of the previous action potential. So this is what a Poisson distribution looks like. The probability of seeing n spikes within a time window of length t is given by this, where r is the one parameter of the Poisson process. The rate parameter, the mean firing rate, and just a couple examples of what a Poisson process might give you. So if this is the rate times the time window, in other words, the expected number of events of spikes, and plotted here is the probability of seeing n spikes. When n equals 0, the probability of seeing 0 spikes when your expected number of spikes is 0 is 1. And as your expected number of spikes increases, the probability of seeing 0 spikes drops off quite quickly. Now, the probability of seeing 1 spike when your expected number of spikes is 0 is 0. But the probability of seeing 1 spike climbs quite quickly, peaking out at around 1 expected spike before dropping off. And as the number of spikes increases, this distribution flattens out and shifts to the right. A slightly different way of looking at this distribution, if you plot the number of spikes against the probability of seeing that number of spikes, given that the rate parameter is 10, the dots show the Poisson values for many different numbers of spikes actually observed, and the line shows a Gaussian fit, which is quite a good fit. Yeah.
So I understand, how can the probability be 1 when n is 0?
You're talking about here?
Yeah.
So if your rate parameter times time is 0, that means that either your rate is 0, so you'll never fire any spikes, or your time window is 0, so it's an infinitely small window which has room for no spikes. So in this case, you'll always see 0 spikes, and the solid curve traces out the probability for seeing 0 spikes, and probability for seeing 0 spikes when you expect to see 0 spikes is 1. Does that make sense? So the probability, so this solid curve is at 1, where RT is 0, and all of the other curves corresponding to 1, 2, or 5 spikes are at 0 when RT is at 0. So when RT is 0, you'll always see 0 spikes. So probability of n equals 0 is 1. The probability for n greater than 0, for n equals 1, for n equals 2, for n equals 5, for n equals anything is 0. Does that make sense? Yeah, it's a little bit of a complex figure. But okay. So just a few properties of a homogeneous Poisson process. And by homogeneous Poisson process, I mean the rate parameter is constant. There are also inhomogeneous Poisson processes in which the rate parameter can vary with time, and those will be useful for modeling firing rates that change. But just for starters, for a homogeneous Poisson process, the mean interspike interval, tau, the expected value of tau, is 1 over the rate. This makes sense. Spikes are temporally uncorrelated with each other. If you expect to have 10 spikes in some unit of time, you expect to have that unit of time over 10 space between spikes on average. The variance of the interspike interval is 1 over r squared. And again, this falls out quite naturally from the definition. And the coefficient of variation, which is the standard deviation divided by the mean of the interspike intervals, is 1. Now you can also look at the Fano factor, which is the variance divided by the mean, and if you do that not for interspike intervals, but for spike counts within a window for a homogeneous Poisson process, that's also going to be 1. In other words, for a Poisson process, the variance in the spike counts is equal to the mean of the spike counts. So how well does a Poisson process actually describe neural data? Usually pretty well. So this is an example from a large number of cells recorded in area MT of the monkey. And here we have the mean firing rate and the variance in firing rate plotted against each other. It's actually spike count over about a quarter of a second. And the diagonal line shows where variance and mean are equal. And you can see that the actual neurophysiological data fall roughly along this diagonal line. So that suggests that a Poisson process is a pretty good description. You can also fit a couple of parameters. So you can look at variance as a multiplier of the mean raised to some exponent. And if you fit these two parameters to this data set, you see that both the multiplier and the exponent stay quite close to 1, regardless of the time window in which you count spikes. So whether you count spikes within a few milliseconds or many hundreds of milliseconds, it looks fairly close to Poisson. One point of deviation between a Poisson process and actual neurons is that neurons are refractory. So what this means is that if a spike is fired, it's extremely unlikely or impossible for that neuron to fire another spike within some short period of time, a few milliseconds typically. So here we have actual neural data, again from monkey MT, showing the interspike interval plotted in a histogram. And you can see that the majority of interspike intervals are relatively small, but at the smallest possible interspike intervals, there are actually no examples. In contrast, a pure Poisson process, this would look like an exponential curve. So one thing that you can do is just explicitly, if you're generating a spike train using a Poisson process based on some rate parameter, you can explicitly add a refractory period. So if a spike occurs too soon after an earlier spike, you can either shift it later or move it altogether. If you shift it, preserve the firing rate at the expense of a little bit of the pure Poisson nature. If you move it altogether, you're going to lower your firing rate a bit. There are more sophisticated ways of keeping both of those, but I won't get into that. So this is a spike train generated from a Poisson model with stochastic refractory period added. You can see that it quite nicely recapitulates the observed data. Another thing that you can do is, instead of drawing your interspike intervals from a Poisson distribution, you can draw them from a gamma distribution. So that adds some factor k here. And when k equals 0, this is exactly a Poisson distribution. When k is greater than 0, you see this refractory period arising. So this is sort of a common way to model a spike train if the underlying cellular level biophysics aren't that important to you. You just want something that reflects spikes with some firing rate, possibly the time-varying firing rate. So next I'm going to take sort of a hard left turn and talk a little bit about how we think about information being measured both across time and across multiple neurons, since brains operate in real time and contain many neurons. Sometimes it's useful to move beyond single neurons and stationary firing rates. One very basic way to get at questions of timing is to look at autocorrelation of a spike train or firing rate time course. So what's typically called an autocorrelation would perhaps more properly be called an autocovariance, because you use mean subtracted spike trains, but you are just taking the expected value of the product of a mean subtracted spike train itself, shifted with varying time lags. And here you see the autocorrelation functions of two different neurons in cat V1. And at time lag tau of 0, there's a strong peak. That makes sense. You're comparing a spike train against that same spike train shifted by 0 milliseconds. It's itself. So there's always going to be a peak at 0. But what you also see, particularly in this bottom autocorrelogram, is this strong oscillation. And what this means is that the particular spike train in question has strong correlations with itself 25 milliseconds later and before, and 50 milliseconds later and before, and 75 milliseconds later and before. Another way of thinking about this is the firing rate is oscillating at 40 hertz. In other words, a 25 millisecond period. And again, that's happening to a lesser degree in this cell. You can also compare the firing rate trajectories, spiking profiles of two different cells in what's called a cross-correlation or cross-correlogram by replacing row and row with row 1 and row 2, two different spike trains. So if you compare the two spike trains whose autocorrelograms are shown here with each other, the cross-correlogram looks like this. And so you can see that not only are these two cells firing, not only are they exhibiting a oscillation in the firing rate, both at the same frequency, but they're actually even at the same phase, because the peak here is at a time lag of 0. So this gives a very basic way of comparing time courses of two different cells. Now, whether these kinds of things are important or not has been discussed a whole lot. And you can coarsely divide studies of neural coding into two paradigms. And I'm going to do this very crudely at first and then try to get a little bit into the nuances. But if you're looking at a single neuron, and you're looking at its activity over time, an independent spike code holds that the only thing that matters in terms of the information being carried by this neuron is the firing rate of this neuron as it changes over time. The specific moment at which any given spike happens is not important. That's just an epiphenomenon, these fluctuations in the firing rate. Alternatively, it may be that correlations between spike times carry additional information. So a burst of spikes may carry special importance, or oscillatory activity may carry special importance. Now, ultimately, any given pattern of firing can be represented to any arbitrary degree of specificity by a time-varying rate code or independent spike code whose rate varies quickly enough. So this sort of distinction breaks down often, and this becomes a question of, well, what sort of time course are we talking about in terms of how quickly does the underlying rate vary? And then also people who would argue for an independent spike code, wouldn't say, oh, oscillations don't happen or bursts don't happen, but rather that we can get the majority of the useful information merely from looking at changes in firing rate rather than looking at the individual spikes. And there's a similar dichotomy if you look at multiple neurons and look across them. So an independent neuron code holds that action potentials between two neurons or multiple neurons in a circuit or a population, the specifics of those action potentials across neurons don't carry any additional information. Again, it's just the firing rate trajectories of the constituent neurons. Alternatively, there may be some extra information present in neural synchrony if two neurons fire spikes at the same time, or if they fire spikes reliably one after the other with some fixed latency, or if they're oscillating at a similar or the same frequency. So these sort of issues are very fundamental, verge on the philosophical. Yeah?
But you know they're not independent. I mean, one fires, the one that's has synapses to fire also, so you know.
Right, yeah. So I should be careful there. If you have, just to take a very for example, if you have one cell that has an axon, one synapse onto another cell, and that synapse is 100% effective. So whenever this cell fires, those spikes are correlated very tightly, but there's no additional information present in that correlation, right? So the fact that this cell fired and then 3 milliseconds later this cell fired tells you nothing more than just the fact that this cell fired. Does that make sense? Okay, so with that brief detour over, we're going to return to reverse correlation and use reverse correlation to estimate or predict how a neuron might respond to an arbitrary stimulus. So the basic problem is we want to estimate the firing rate as a function of time. So this is a varying firing rate. So we're going to do that by assuming that there's some baseline firing rate, and then there's some kernel that's being convolved with the stimulus. Now, what is that kernel? Well, it's something that we have to estimate. In order to estimate it, we're going to minimize the error. In other words, we're going to minimize the difference between our estimate and the actual firing rate. And we want to, in order to minimize this, you can set the derivative of this to 0, or equate the derivative of this to 0. And when your stimulus is white, in other words, when there's no temporal autocorrelation in your stimulus, solving that becomes fairly straightforward. And it turns out that your kernel d of tau is the spike-triggered average times the mean rate divided by the variance. When S is not white, things get a little hairier. At the very end of this, I'll briefly touch on a technique for dealing with that case. But since the stimulus is under your control, if this is what you want to do, it's definitely easier to use temporally uncorrelated stimulus. Now, earlier somebody asked about, well, what if the firing rate is a nonlinear function of the stimulus? So you can still estimate the kernel as before, and then this convolution of kernel with the stimulus gives you what we'll call L of t, the linear part of the response. And you can then simply add some nonlinearity by taking some function f of that linear part and adding that to the baseline firing rate. It's not, so there are a couple of different ways that you might decide, oh, I need f. One is if you're building a model, and you can say, well, I want neurons that don't fire until some threshold is crossed, and then they increase their firing rate linearly, or something similar. The other is to actually plot observed firing rate against L of t. And then you might see something that looks like this, or looks like this, or looks like this. And then you can say, oh, well, you know, that looks like this sort of nonlinearity. Let's fit a rectified linear function or a sigmoid or a rectified hyperbolic tangent to the data and use that as our nonlinearity. So yeah, I mean, these are just a few examples of things that are commonly seen physiologically. So up until now, we've been talking about how to measure and describe firing rates as a function of stimulus. And the second part of this talk is sort of the reverse question of, say we have some firing rates, and we want to know what stimulus is likely to have elicited those firing rates. In other words, decoding. And at some level, this is what the brain does, right? I mean, there are neurons firing there, and somehow, based on the activity of those neurons, we're somehow understanding what's out there. So first, a few basics. So we've got a vector R. This is just a vector of firing rates for most of the rest of the talk. And in particular, there's stationary firing rates, so this is just a vector of scalars. This is the response that we're working with. We're trying to go from this to some estimate of what the stimulus was that elicited this. So we've got P of S. S is the stimulus. P of S is the probability of stimulus S being presented. This is also known as the stimulus prior. Getting a little feedback. P of R is the probability of response R being observed, the response prior. P of R and S is the probability that S was presented and response R was observed. This is also called the joint probability between R and S. Here we have P of R given S, the conditional probability that response R was observed given that stimulus S was presented, and P of S given R, the conditional probability that stimulus S was presented given that response R was observed. A little bit of probability arithmetic. The prior probability of a response is equal to the sum over all stimuli of the probability of each stimulus times the conditional probability of the response given that stimulus. So if there's a particular stimulus that's very common, now, again, in laboratory experiments, you often want your priors on stimuli to be uniform, but in the real world, they're not. So P of S, where S is a face, might be relatively high. P of S, where S is a unicorn, might be much lower. And if you want to know what's the probability of a given response, well, the probability of that response given a unicorn is going to be weighted much less than the probability of that response given a face. Similarly, P of S is equal to the sum over all possible responses of P of S given R times P of R, and for corresponding reasons. Up until now, we've been considering how to estimate P of R given S. We know what the stimulus is. We want to know what's the response likely to be. Now we want to talk about P of S given R. And given this, and this, we can use Bayes' theorem. And we find that probability of S given R is equal to P of R given S times P of S divided by P of R. And we'll get into a little bit more about how to use this in a moment. In particular, we'll do that in the context of two-way decoding. So perhaps the most basic kind of decoding task is a two-way discrimination task. So here's one classic example. Your goal, or the monkey's goal in this case, is to indicate which of two possible directions an array of moving dots is predominantly moving in. In some cases, every single dot is moving with the same velocity. The task is then very easy. In other cases, the dots have 0% coherence. They're all moving with random velocities. The task is actually impossible. In between, you can have any level of coherence. Here, 50% coherence, half of the dots are moving with the same velocity, one of two possibilities in the experiment, and the other half are moving with random velocity. So this experiment was run upwards of 30 years ago, and monkeys performed it as a behavioral task, indicating which of two directions the dots are moving, while neurons in monkey MT were being recorded. And in a given experiment, with a given neuron, the direction of motion, the two directions of motion corresponded either to that particular neuron's preferred direction, in other words, the direction that elicited the maximum firing rate, presumably established using some of the techniques that we've just talked about. And then the other direction was the opposite direction, also called the anti-preferred direction. So how did the monkeys do? Here we have plotted on the x-axis the percent coherence, and on the y-axis we have the fraction correct. These black dots show the monkey's behavior, and there's actually a typo here. This should be 0.4, this is 0.5. So at very low coherence, below 1% coherence, the monkey's performance was at chance. And by about 10% coherence, the monkey's behavior was at ceiling, 100% correct. And in between, you see this nice sigmoid psychometric curve. Based on the neural data, you see a very similar curve. The neuron was very poor at predicting which direction the dots were moving when they were moving with very low coherence, and they're very good at predicting which direction the dots were moving when they were moving with relatively high coherence. So how is this neurometric tuning curve created? So bear in mind that the dots were tuned to align either with the neuron's preferred direction of motion or its anti-preferred direction of motion. Here we have histograms as a function of firing rate, showing how frequently the neuron responded with a given firing rate when the dots were moving in the anti-preferred direction versus when they were moving in the preferred direction. And you can see with 12.8% coherence, these two distributions overlap almost not at all. When coherence drops to 3.2%, the two distributions, firing rate in response to anti-preferred direction versus firing rate in response to preferred direction, overlap a fair amount, and at a 0.8% coherence, they overlap almost entirely. So one thing that you can do is just draw a line between these two distributions and say, all right, if the firing rate is less than this line, less than this threshold, we'll say that things are moving in the anti-preferred direction. If the firing rate is to the right of the threshold, we'll say that things are moving in the preferred direction. Your ability to discriminate between these two distributions in such a manner is called D prime. And D prime is very easy to calculate as long as the two distributions are Gaussian and have the same variance. When that's true, D prime is just the difference of the mean rate in the positive condition minus the mean rate in the negative condition divided by the standard deviation. So in other words, how far apart are these two peaks in standard deviations? Just the distribution of firing rate. For, in this case, the anti-preferred direction and the preferred direction. Does that make sense?
Distribution over trials?
Yeah, so this is a histogram counting the number of trials. So each black bar here shows the number of trials in which the corresponding firing rate on the x-axis was seen. So in the anti-preferred direction, you saw a firing rate of, let's say, 5 hertz in about 8 trials, and you saw a firing rate of 11 hertz in about 17 trials, and so on. So yeah, it's that kind of distribution. Does that make sense? Okay. So we're using those firing rates to predict which of the two stimuli was shown for one neuron. Yep. And this extends to multiple neurons in a relatively straightforward fashion, but this is one. So D prime is a statistic that comes to us from signal detection theory, which I believe originally came from people trying to detect radio signals in the midst of noise. And they had to say, well, is there a signal here or not? Another thing that comes to us from signal detection theory is this notion of the receiver operating characteristic curve. And to make an ROC curve, you plot beta against alpha, where beta is the hit rate of the test. In other words, the fraction of trials in which the condition is positive and you say that the condition is positive. Alpha is the false alarm rate of the test. In other words, the fraction of trials in which you say that the condition is positive, but the condition is actually negative. So in the context of this experiment, the hit rate is the fraction of trials in which the stimulus was shown in the preferred direction, and you say correctly preferred. And the false alarm rate is the fraction of trials in which the stimulus was actually moving in the anti-preferred direction. You say incorrectly preferred. And you can plot this out as a function of that threshold. In other words, as a function of where you draw this line. Do you draw it here? Do you draw it here? Do you draw it here? At many different coherence levels. So at 0.8% coherence, this ROC curve follows the diagonal. In other words, your probability of getting hit is equal to your probability of getting a false alarm. And this might be clear, but when you're in that regime, you don't really know anything about the stimulus. You can get more hits, but the cost is getting exactly as many more false alarms. Alternatively, at 12.8% coherence, remember, you can do very well. So you can get beta, your hit rate, up to about 90% before you start getting any false alarms. And you can get your hit rate up to 100% at the cost of only about 10% false alarms. Now, in between these two extremes, there's sort of a little range. And you may choose, okay, I want to draw my threshold right here, and get, say, 97% hit rate and 2% false alarm rate. But it's still, even if you draw these ROC curves, although it gives you a little more information, D prime, it still leaves some things up in the air as to where exactly the best place to draw your threshold is. And there are some heuristics that you can use that make sense. So you can, for example, choose a threshold that maximizes overall performance. Or you can choose a threshold at the point where the two distributions intersect. Or you can choose to put the threshold halfway between the means of the two distributions. But there is a way of getting rid of that question of threshold entirely, which we'll come to in a moment. So this is another example from the Kremen lab showing the use of signal detection theory in a multi-class decoding scenario by basically converting that multi-class problem into a two-class problem. So for this experiment, data were reported from intracranial electrodes in epilepsy patients, as he described, while those patients looked at images belonging to 5 categories. Now, for each electrode, one preferred category was chosen, and that category was considered in opposition to the other 4 categories. So in this example, the electrode preferred fruit and exhibited larger responses to fruits than to images in these other categories. So here we see the distribution of intracranial field potential responses to fruits in black and to non-fruits in gray. You can see that these two distributions are different and have different means indicated by these dashed lines, but particularly the non-fruit category is not Gaussian and is just a different shape from the fruit category, its distribution. So calculating a D prime here would be a little bit more complicated, but one can still calculate an ROC curve and see that we're well above the diagonal and thereby able to do quite good decoding. So if we want to get rid of that question of threshold, we can use what's called a two-alternative forced choice task. And in this task, rather than presenting your subject with one stimulus and asking the subject to make a binary decision based on that stimulus, you present in a given trial 2 stimuli, one after the other, each, corresponding to the two different classes in your experiment. And the subject's task is to indicate which of the two stimuli corresponds to the positive class. So going back to the direction of motion discrimination, you would present a stimulus moving in the preferred direction, a stimulus moving in the anti-preferred direction, and the monkey would have to say, oh, the first stimulus was the one moving in the preferred direction. So in this case, the probability of being correct is just the integral across all possible thresholds of the probability that the firing rate is equal to the threshold times your hit rate at that threshold. In other words, the area under the ROC curve. Essentially what you're doing in the alternative force choice task is using one of the conditions as the threshold for the other condition. Now, how well does this sort of thresholding do? It turns out that it's possible to do as well as possible. There's a result, it's mathematically provable given some basic assumptions, that it's impossible to do better than what's called the likelihood ratio, which is the probability of seeing a given response, assuming a positive condition, divided by the probability of seeing a given response, assuming a negative condition. So if you calculate this likelihood ratio and use that or some monotonically increasing function of the likelihood ratio as a threshold, it's possible to do provably as well as possible in this kind of two-class discrimination. And just as an aside, this likelihood ratio is equal to the slope of the ROC curve. Okay, so we've talked about two-way decoding, and I mentioned briefly, yes?
I have a question from a bit earlier. So is the Poisson distribution the only distribution with Fano factor 1?
I'm not sure, actually.
I'm not sure. Do you fit the data, you get a 1 and you conclude it's a Poisson process, or is the other way around?
You conclude it's consistent with the Poisson process. So
it might, if it's not the only one with Fano factor 1, it might not be a Poisson process.
I know there are other point processes whose coefficient of variation for a spike interval is 1, that are not Poisson.
So Poisson has some kind of 1, if it's 1, you cannot conclude it. So it has to be a renewal process.
So you can have other point processes with a Fano factor of 1 that are not Poisson processes, but they're also not renewal processes. Okay. So let's talk a little bit more about optimality of decoding. So what is the best we can do? And what does that mean? So we need some notion of best. And one way of establishing that is to come up with a loss function. So you say, all right, well, I obviously want to infer the stimulus perfectly correctly all the time. But say I'm not going to be able to do that. What's the penalty for being wrong? So one common loss function is the squared error, which is just the square of the difference between the actual stimulus and the inferred stimulus squared. If you accept that as your loss function, then getting back to that Bayes framework that we mentioned earlier, the expected loss is minimized by using as your estimate the mean of the distribution. So this is the best you can do, assuming this kind of L2 error. If your loss function is instead the absolute error, just the absolute value of the difference between the stimulus value and the predicted stimulus value, or the inferred stimulus value, then the expected loss is instead minimized by the median. And for other loss functions, it's possible to calculate what is the optimum way to calculate or to infer what the stimulus was. But another way of thinking about best decoding is to ask, okay, well, what was the stimulus that was most likely to have generated the observed response? If we can figure that out, the most likely stimulus, isn't that the best? And yeah, maybe it is. So that takes us to maximum likelihood estimation, which answers exactly this question. So to calculate the maximum likelihood estimate of a stimulus, you solve for SML in this equation, where f sub a is the firing rate function as a function of your stimulus for the 8th neuron in the set of neurons that you're considering, and r sub a is the firing rate of the overall firing rate of the 8th neuron. So set this equal to 0 and solve for S and L. Now, as there are certain classes of function for which solving this is quite easy. For example, if f is a Gaussian, which is a relatively common tuning curve, as we've already discussed. In other cases, you may have to solve this computationally rather than analytically. So one small drawback with the maximum likelihood estimate is that it can be very sensitive to conditions where small changes in the response yield large changes in the estimate. For example, if you happen to get a spike when you're way out of the tail of your firing rate estimate, that's going to give you an estimated stimulus that's rather different than what there actually was. Another problem is that it doesn't reflect stimulus priors. So it may be that on a particular trial, say if you're recording from IT of a monkey who's walking around looking at stuff in his classroom, and you observe a particular firing rate pattern from the assembly of neurons from which you're recording, and your maximum likelihood estimate of the stimulus that elicited those patterns was a unicorn. There are no unicorns here. There are no unicorns in real life. But maybe the firing rate pattern for a unicorn looks pretty similar to the firing rate pattern for a MacBook Pro. And then you might say, oh, well, MacBook Pros are very common in this room. Unicorns are very uncommon. So we'll say that we'll estimate that the monkey actually saw a MacBook Pro. So the maximum a posteriori estimate is an extension of maximum likelihood estimation that includes weights for stimulus priors, so that you don't get nailed by that problem. Now again, under experimental conditions, it's often advisable to keep your stimulus priors uniform, in which case this term is 0 and MAP is exactly equal to ML. But using less constrained stimuli is not always the case. So, say you've come up with an estimator that you like. You want to know how well it's doing. Let's talk a little bit about how we can evaluate an estimator. There's sort of three fundamental quantities, or I should say there are three sort of fundamental qualities in evaluating an estimator. One is bias. And bias is just a measure of, over repeated trials, for a given stimulus, how different is the expected value of your estimator from the actual stimulus value? And we generally like for our estimators to be unbiased, which means if you collect enough data, you'll, on average, get the right value for the stimulus. Another quantity is the variance, and that is the expected variation of the estimator from its mean, trial to trial. This is generally not possible to get 0, and we'll describe that explicitly in a moment, but this is just a measure of how much your estimator spreads from run to run, from trial to trial. And you can actually combine these two terms to arrive at the expected estimation error, which is just the expected squared error between the estimator and the true value. And that's given by the variance plus the bias squared. And again, under the case of a zero bias estimator, that's just the variance. So I said that I'd give you a bound on the variance, a lower bound, and I will keep my promise. So the Kramer-Rao bound, which is a function of the derivative of the bias and what's called Fisher information, sets such a bound. It's impossible for the variance to get below this quantity. Fisher information tells us how much an observed random variable, for example, firing rate, can tell us about a latent parameter, for example, the stimulus. And it can be calculated several different ways. One way is the expected value of the negative curvature of the conditional probability surface of your firing rates with respect to your stimuli. So it's generally impossible to get zero variance unless you can get perfect Fisher information, which in the real world never happens. So the maximum likelihood estimate, when I introduced it, I said, well, this makes sense for saying what's the most likely stimulus, but it also has some nice properties in the context of what we've just been talking about. One is that as the number of neurons that you're considering in your maximum likelihood estimate increases, your estimate can actually get arbitrarily good. So the expected difference between the estimate and the true value can be made arbitrarily small. It's also an unbiased estimator. So this is zero. So we just have 1 over the Fisher information. And it actually attains the Kramer-Rao bound. So the variance is actually equal to 1 over the Fisher information. So it's very efficient. Zero bias, minimal possible variance. So it's, in that sense, optimal. All right. Finally, I'm going to take the last few minutes to talk about how we can decode not from a vector of scalar firing rates, but from an actual spike train. And this is going to recall some of the earlier stuff we talked about with reverse correlations and spike-triggered averages and kernel convolutions. So the basic cartoon of the procedure I'm going to sketch out first. So you have, let's say you have some stimulus, some one-dimensional stimulus in this case, varying with time. And the stimulus is eliciting a spike train. And you want to be able to predict what the stimulus was at time t based on spikes leading up to time t. And in one sense, this is a little bit of a funny thing to do, because the spikes are actually being fired in response to the stimulus, and yet you're using spikes up to the stimulus in order to predict the stimulus. So this only has any hope whatsoever of working if there's some temporal correlation with the stimulus. And yet, this is kind of what the brain does, right? I mean, it is predicting what's out there, what the stimulus is, based on spikes that have happened. Now, the brain allows itself a little bit of latency, so we'll do ourselves that same favor. And we'll actually, at time t, be predicting the stimulus at time t minus t naught, where t naught is our prediction delay. So you can think of this as maybe the amount of time that it takes for information to get from the ret to IT to prefrontal areas. And so the basic idea is we're going to take all of the spikes up to time t, and everywhere that there is a spike, we're going to insert some kernel. And then at time t, we're going to add up the value of that kernel. And that's going to be our estimate at time t minus t naught. So there are 3 example spikes here, spike number 4, number 7, number 8. Spike number 8 happens after time t, so its contribution is going to be 0. Spike number 7 happens after t minus t naught. So this is actually a spike that we think might have been caused by the stimulus at t minus t naught. but it happens before time t, so it's still admissible in our decoder. And just as an aside, I should have said this earlier, one of the reasons we might want to build a decoder like this is to perform real-time decoding based on a neural spike train, set of spike trains. And finally, spike 4 happens well before t minus t naught. So it may tell us a little bit about what's going to happen, but to the extent that it does, that's only because of the temporal correlations in the stimulus. Now here's the kernel that we're using. Here it is, again, larger. And here is the spike-triggered average for this toy data set. You may notice some similarity between these two. In fact, the kernel is exactly the spike-triggered average reversed in time. So notice the tau axis, the time axis here is running in the reverse of the usual direction, shifted by tau naught. So negative 160 milliseconds moves over, and set to 0 for tau less than 0. And this works in some cases. Given the time, I think I'm not going to run through this math, but the basic setup is we have some kernel that we're convolving with our spike train, and we're using that convolution to get an estimate of the stimulus at time t minus tau naught. We want to optimize this kernel. Optimizing the kernel means minimizing the squared error between the estimated stimulus and the actual stimulus. If the spike train is uncorrelated with itself, which is realistic when firing rates are low and the time window of consideration is small, then the optimal kernel is just the spike-triggered average at tau naught minus tau, exactly as I described pointing at the cartoon. Spike-triggered average, temporal reversed, and shifted by tau. Shifted by tau naught. Things get more complicated when the spike train is not, when the spike train is correlated with itself. In that case, you can use spectral techniques involving the Fourier transform of the rate stimulus correlation and the spike train autocorrelation. And the derivations of all of that are in this book. I believe around page 110. But it's a pretty slick trick. And using this sort of decoder, we can do very well. So here's one example from the visual system of one of nature's most robust spheres, the fly. This is from these are data recorded from neuron H1 in the fly visual cortex, which is sensitive to horizontal motion. And here we have plotted the velocity of the visual stimulus being presented to the fly, or neurons being recorded from. And here we have the optimal kernel as calculated using this technique. The dashed line is the reconstruction of the stimulus using this kernel convolution technique. And you can see this does quite well based on a spike train at reconstructing what the stimulus was that elicited that spike train. So, we know that stimuli elicit spike trains in the brain. We've seen how we can go from spike trains to spike counts, relatively straightforward. We've also seen how we can represent spike trains as firing rate time courses. We can use spike counts or firing rate time courses to generate spiking models, which can give us data to test or debug or model things. We've also seen how we can go from spike counts back to estimates of the stimuli. And most recently, we've seen that we can also go from spike trains back to stimuli, decoding directly from spike trains. So we can move around this diagram with some fluency now. I wouldn't say that we therefore understand everything about how the brain works, but we've at least got some tools that are useful to approach it. Yeah?
I got a little confused you go back one slide.
Yep.
So confused and what exactly we're trying to do here. So you can put a voltage meter in the neuron and measure the spikes.
Right. So we've got spikes here.
And we know what we're putting in front of the fly, and that's the dotted line on the bottom there.
I believe actually the stimulus is the dash, is the solid line.
Solid line. Okay.
But I might have that backwards.
I think that you're doing some kind of deconvolution and you're getting some impulse responses there at the top.
So this,
I don't know what to do with that.
So this is the kernel that we've estimated.
The name.
So that's this kernel, which, if the spike train has no autocorrelation, we can estimate at the reverse correlation, the spike-triggered average.
But even if you do it perfectly, what does it mean physically? What do I do with that? What can you tell me?
So what you can do with that then, once you've generated this kernel, you can then continue recording from this same neuron. So you're no longer controlling the input to this cell. And you can, based on the spike train, you can infer what the visual stimulus that the cell is receiving is. So you can do real-time decoding of the stimulus based on the observed spike train. Does that make sense? And there are other ways of doing real-time decoding from spike trains. People have used Kalman filters for that. Particularly in the realm of neuroprosthetics, there's been a lot of work. But this is one useful technique.